Great. So let's start, dear student. Do not forget to put plus on the YouTube okay, for your assistance. So we finished with exercise number. Let me check. Yes. So the next one is exercise 5. So this is number 5. We have to complete this one, and in order to complete this one, so applying the least number principle, prove that for every two natural a and b, so we have two naturals, a and b are natural numbers, and b is greater than 0, and we have to prove, so prove that there exist R and Q naturals such that A is equal to B Q plus R, and R is at most B and greater than 0, right? No, it's less than B and at least 0. So we have to prove two things. In this case, we have to prove the existence of such R and Q, and okay, so we can add here, and R and Q are unique. So we have to prove that these two numbers R and Q exist and that they are unique. It means that, okay, so proof. So we need to prove both existence and uniqueness. Okay, so first of all, let's prove existence. So let's prove that the existence of R and Q, right? So look at the equation here, and we can see that this is, so we have the equation A equal BQ plus R, and this is the same as writing R equal A minus BQ, right? These are exactly the same. So we can say, we can conclude that any remainder, so R here, so R is the remainder, right? Any remainder R can be expressed by this formula here, so A minus BQ, okay? And then, okay, and now let's then fix some set. So let S be a set, be the set of all reminders. So S is the set of all reminders. So S, we can write it in the following way. S is equal to all such number A minus B Q prime, where Q prime is a natural number, right? And then we can see that, so we have, okay, so all the, so this is the set of all the reminders, and this, so the set of all the possible R that we have, right? And this set is a subset of the integers, right? Because we have here minus. So maybe we can get not only natural numbers, but we can get integers as well, right? So this is a subset of the integers numbers. So I believe that you know what the natural number is, what the integers are, and so on. Now, that's it. Okay, so we have this set. Now we have to apply the least number principle, right? So we have to apply the least number principle to prove that these two numbers exist. So let's remember that the least number principle is the following. In the case when we are working with sets, we say that for all subset of the wait. Oh, we still don't have to do this. No, we still don't have to do this. Now, so S is a subset of the integers, but we need another set. So let T be the set of the intersection of S with the natural numbers. Okay, so T is going to be this set, but only for which these numbers are natural. Okay, not all the integers that we have here, but only the natural numbers, T. Okay, and now we can apply the least number principle. So the least number principle states the following: that for any subset X of the natural numbers, if X is non-empty, right? So and if X is non-empty, then there exists the minimum of X. Okay, so it means that if we have some subset of the natural numbers, like in this case T, so T is a subset of the natural numbers, right? It means that there exists some element that belongs to X such that is the minimal element in X. Okay, and yes, and then we need to apply this to this set. So we have that T is a subset of the natural numbers. Yes, this is check. Now we have to check that we have to check that T is non-empty, right? We have to check that this set T is non-empty. So we have to check that this S for natural numbers is non-empty. And we can see that this is non-empty because if we take Q prime equals 0, right? If we take Q prime equals 0, then we obtain A minus B times 0 is going to be A. So A belongs to S, right? And A belongs to T as well, because A is a natural number, right? So A, by the condition of the problem here, we have that A is a natural number, and then we have that A belongs to S, but A belongs to T as well, right? So A is a natural number. Then it means that then T, of course, is not empty, okay? Because we already found some value A which belongs to T, and we know that A exists. Since A exists, then we conclude that this is not an empty set, okay? So we have that this condition holds as well, and now we can apply the least number principle to this set. Then by the least number principle, there exists R, which is the minimum element of T. Okay, so now we know that there exists some minimum element of this set T. Let's call it just R. Okay, so we fixed R as the minimum element of T. That's it. So we have this by now. Now we need to show, so let's show that this R is the remainder we are looking for. Right, because we have to prove that this R exists. We have to prove that this R exists, and we already have proved that. So we have shown this, and we have shown that for this set we have some element R, and now we have to choose that this R is the remainder that we are looking for, that we say that exists. Okay, now okay, so since R belongs to T, so R is an element of T, then there exists Q natural such that R is equal to A minus BQ. Okay, so we have that R is an element of T, and since T is this set, then there exists some Q such that R is equal to this. Okay, so there exists some Q natural such that R is equal to A minus BQ. Okay, and noticed that R is greater than 0, right? Because R is greater than 0 because R is greater than 0. Why is R greater than 0? So we have A minus BQ here, and is the minimal. Yes, and R is the minimum is the minimum element of T, right? And then wait, why is 0? Why is 0? Why is greater than 0? No, it's greater or equal than 0. Yes, greater or equal than 0. That is what we need. Yes, of course. It can be 0 because R is natural. Then R is at least 0. Okay. Now, okay, so we found that we have some R, and for this R we have this. So for this R there exists some Q. Okay, and R is at least 0. Now consider the next smaller remainder than R. Okay, so we have to consider the next smaller remainder. What does it mean? What does it mean? It means that we have to take A minus B, and we put here Q plus 1. Okay, so we had R. Okay, R is equal to A minus BQ. Okay, and now we have to consider the next smaller. Then we have to put A minus B Q plus 1. So we have here Q. Now we consider Q plus 1, and we can see that this is an element of S, right? So this is an element of S. This Q plus 1 is just any Q prime. Okay, just Q prime is equal to Q plus 1, and this is equal to R minus B, right? So we have A minus BQ minus B, right? and A minus BQ is equal to R, then we have R minus B. Okay, so we have that R minus B is an element of S, and since R is the minimum element of T, and R minus B, so R minus B is less, of course, is less than R, then is R, then R minus B doesn't belong to T. Okay, so what does it mean that R minus B doesn't belong to T? It means that this is an integer, so this is that R minus B is not a natural number, that this is I don't know, -5, -2, any negative integer. Okay, so we have that R is the minimum, right? And we also have that R minus B is less than R. Then R minus B doesn't belong to this set. So R minus B belongs to set. So R minus B can be an integer, but we see that R minus B is not a natural number, right? So it means that this is some negative integer. Then this implies that R minus B, as I told you, is less than 0. So R is less than B, right? So if we have that R minus B is less than 0, it means it's the same as saying that R is less than B. Okay? And now, what have we obtained here? Look, we obtain that there exists some set T, right? So we obtain first of all that there exists some set T, non-empty set T, in which we found some R. We define this R, and then we say that if we have that R, then we have that there exists some Q such that this holds, right? And R is at least 0, and moreover R is less than B. So this is all we had to prove here. So we proved that there exists some R for which there exists some Q such that this holds. So R is at least 0 and R is less than B. And that's it. So this we proved the existence of R and Q. So here we were proving the existence. Okay. So now we proved the existence. That's very good. Now we have to prove the uniqueness. So the existence is checked. Okay, the existence is checked. Now we have to prove the uniqueness of R and Q. Right? And let's do that. So let me just guess this one. So if you have any question, you can write a commentary or something. Maybe I can read it, but I know how difficult is that. So why R minus B? What R minus B? Why this? Well, R minus B. Look, R minus B is less than R, right? Then since R is the minimum, it means that R minus B doesn't belong to T, because the last, the minimum reminder we had is R. It means that R minus B is a reminder. Do not forget that R minus B is a reminder, right? Then it belongs to S, and it means that r minus b is less than 0. Okay, I hope that is clear somehow. Okay, so now we have to prove the uniqueness. So uniqueness. Okay. So if we want to prove the uniqueness, what does it mean? That if we have some q and some r, then for which this hold, right? Then if we have a different q and a different, so some q prime and some r prime, then the a and b should be different. Okay. So by contradiction. Okay. So by contradiction, let's prove this. Then assume that. So let's assume that this is not true. And what does it mean that this is not true? It means that we have q and r and some q prime and r prime, such that what holds? Such that we have a plus b q plus r and a plus b q prime plus r prime. Okay. So if this is not true, if they are not unique, it means that we can take two different values for each q and r, and this should be true for the same values of a and b, right? So here we have that r is less than b, and here we have that r prime is less than b as well. Okay. So assume that this is true. Then we want to show, what do we want to show? We want to show that q is equal to q prime and r is equal to r prime. Okay, so we want to show that q is equal to q prime and r is equal to r prime, right? Then we have here a equal this, and we have here a equal this. Then this is equal to this, right? It means that bq plus r is equal to bq prime plus r prime, right? So it means that bq prime minus q plus r prime minus r is equal to 0, right? We just put all these elements to this side, and well, actually this element to this side, and okay, so we obtain this. Somehow we need to show that that this is true if and only if they are equal. So q prime is equal to q and r prime is equal to r. And we have this condition here. So let me write this condition better here. So we have that 0, r, and b, and we have the same condition here. So since we have that r is between 0 and b, and r prime is also between 0 and b, then what can we say? We can sum up this. So it means, well, actually we can't find the difference. Well, the difference of r minus r prime is going to be who can tell me what should I write here and what should I write here? So what should I write to the right side? And what should I write to the left side? I will be waiting for. So look, we have this condition. Then it means that the difference of r and r prime should be between, what are the boundaries here? What do you think? You can write in on YouTube. So yeah, b minus b. Okay, so we have here b, and here we have minus b. Okay, so in that case, when we have b and 0, 0, b, so on. So we have that the difference r minus r prime is between minus b and b. And it means that what? It means that r minus r prime over b is between what? Is between 1 and minus 1, right? So we just we divide everything by b. So we obtain this, okay? And this, from here, you can see that r minus r prime divided by b over b is equal to, from here, is equal to, wait, yes, this is equal to a minus a prime. No, a prime minus a. Okay, so this is equal to a prime minus a. And we have, so let me write that over there. A prime, no, what I'm saying, q prime, of course. Q prime minus q, yes, from here, right? This side be to this side, and then we have q prime minus q. Yes, now it's correct. Now what does it mean? I have that this number, so we have that q and q prime are both natural numbers, right? And the difference between them is between 1 and, well, between minus 1 and 1. What does it mean? That, so I have that, so q prime minus q is between 0 and 1, between minus 1 and 1. Then this is true if and only if what? Why did we take minus b and b? Where did we take minus b and b? Ah, here. Here, you mean? Right. Well, you just have to check this, okay? And yes, q minus q prime should be, so q prime minus q should be 0. Right, because we have a natural number here, we have a natural number here, and we know that these natural numbers, so these differences should be a natural numbers, should be an integer, actually. An integer between minus 1 and 1, so is 0, of course. This is the only solution for this case. And then, if we put 0 here, so we put that this is 0, right? We found that this is 0. It means that r prime minus r is equal to 0. Well, then r prime minus r is equal to 0. And that's it. So we proved that if we have for some a and b, for some fixed a and b, we have two different values for q and for r. We obtain that they are going to be the same. Then r and q are unique. Okay, so is everything clear here? Well, I hope it is. Now we have to move forward. I think I can erase this as well. I will need it very soon. Now this is going to be exercise number 6. So I'm not going to write everything because it's a long condition here. So we have at the point 0. So we have the line from 0 to infinity, right? This is going to be, well, it's the real line, but for us it's going to be just like a rod, okay? And there's a car. There's some car here. Some car. So there's a car here in 0 position. And an infinite. So we have here some infinite reservoir of fuel. So we can take any amount of reservoir as fuel as we want from this reservoir, okay? And the car can move for up to 100 miles. So if we divide this into miles, we have here 100 miles, right? Kilometers, miles, it doesn't matter. So 100 miles here. So we know that if the car can move 100 miles without refueling, okay, the tank, right? And we can save, like put some fuel in the way. In any place here we can put some fuel here and any place we want, okay? Or so we can put and then we can take this fuel from here. And then we have to prove that it's possible to drive to any point of the half line, so that we can with these conditions we can get this car into any point, right? Any point, right? Any miles you want, you can do it. So we have to, so let's solve this problem. Of course we are going to solve this by induction, but let's first look at the problem. So we have, so who can tell me what's the distance that the car can't, so if we want the car to go forward and back, I mean to go to some point here and then get back to the initial point, what's the maximum point that the car can reach here? So we have that if we go to 100 miles, the car can get to 100 miles, but in that case we don't have any fuel. So the tank, the car's tank will be empty in this case, right? So we can move 100 miles, but then we are going to be just here, and this is going to be the last stop, and that's it. We cannot move anymore. But what if we want to move, and then we want to, the maximum point to which we can move, and then go back to the initial point? Who can tell me what is the maximum point here? that we can't spend all the fuel, and we can go and then back. So of course this is a number in miles, so we have that this is 100 miles, but at what point we can go and then back? What do you think? Nobody? So what if we go 50 miles? We can go 50 miles in this direction, and then we can go back 50 miles, right? Yeah, 50. Somebody got 50. Yes. So we can go 50 miles and then go back 50 miles, but we cannot put any fuel here. So if we left some fuel here, then we cannot reach the initial point again. So yes, what if we want to? So if we want, for example, to put some fuel here. What if we reach mile 49 miles? How many units of fuel can I put in this mile, in the 49 miles? Hmm? 2 units, right? So I can go 49 miles. Then I put here 2 units of fuel. I mean, enough fuel to go another 2 miles, and then go back to the initial point, right? And what if, for example, this is the car here, and I go just 1 mile, just 1 mile here? How many fuel can I save here? 98, right? 98 units of fuel. So I go here, and so I spend 1 unit going and 1 unit going back. So I spent 2 units at all, and then it means that I can put in this point, in the first mile, I can put 98 units of fuel. Yeah, and so that's what we had to think when we look at this exercise, right? And now we have to prove that knowing all this, we can reach any point we want, right? So how are we going to prove this? Look, we have to prove that if we can reach any, so if we can reach any, so n minus 1 miles. So if we can reach n minus 1 miles, n is any number. So if we can reach n minus 1 miles, then we can reach n miles, right? So we have to prove this by induction. So we have to say, if we are able to go n minus 1 miles, then I will be able to go n miles. But what's the problem here? That maybe we can go n minus 1 miles. We know this for sure. And then I tell you, yes, you went n minus 1 miles, but your fuel, it's over. So you don't have fuel anymore, right? So you get to n minus 1 here, but your tank is empty. So the assumption of the induction is holds, right? Because we get n minus 1, but it doesn't mean that we can reach n miles, because maybe here the tank, the car's tank is empty. So what do we need to prove actually? We don't need to prove this. We don't need to prove this. We need to prove that if if we can reach, no, if we can put as much fuel as we want, and at n minus 1, then we can do the same at position, or yes, at position n. So all we have to do now is not just getting into, I mean, n minus 1 miles far away from the beginning. We don't have just to go there. We have to go there and put in this position as much fuel as I want. Okay, so a lot of fuel. I don't know. So remember that we have here an infinite reservoir of fuel. So we can take as much fuel as we want, and we can go to this point and create some kind of infinite. So here is going to be like some infinite reservoir of fuel as well, so that we can take as much fuel as we want from this point, to n minus 1. In that case, we will know 100% that we can go to the position n, and that we can put in position n as much fuel as we want. Okay, so let's prove this. Okay, so in the basic step, the basic step is what? Is for n equals 1. So for when we have here 0, we have here 1. This is the car. And then I told you that in the first trip, I can put 98 units of fuel, right? And then we can go and then back, and then we can go and back again and put another 98 units. And we can do this anytime we want, anytime we need. Okay, so this is good. Here will be any amount of fuel that we need. Right? So for n1, this holds, right? We can do this, of course. Now, what if, so the induction step is that assume that in n minus 1, so at n minus 1 miles from the start, and here I have to write this, so I put as many fuel as I wanted. Then at n miles, I can put as many fuel as I want. And that's it. If we do this, it means that we can reach any point in this half line. Okay, so again, let me review this. Here at the beginning, maybe you can think that we have to prove that we need to, if we know that we can reach the n minus 1 miles, then it means that we can reach n miles. But what if, for example, we reach n minus 1 miles and our tank, the car's tank, is empty? So this is not going to be true. So we need to prove this, that if we can put as much fuel as we want in at n minus 1 miles from the start, then we can put as much fuel as we want at n miles from the start, and then we can reach any point we want, and that's it. Okay, good. So this was exercise number 6. Now let's do exercise number 7 here. So, exercise number 7. So we have to prove that 1 plus 1 over 4 plus 1 over 9 plus so on plus 1 over n squared is less than 2 for each and at least 1. So we have to prove this. Of course, we are going to prove it by induction, but how? So let's look at this sum. So this has to be true for any natural number greater or equal than 1, right? So this sum for any this number has to be less than 2. But what, so let me write this here. So this is just like, okay, so let me write this here. So what if we have 1 over n squared? This is less than 1. We can write this just n minus 1, right? So if I take n minus 1 here, not n, but n minus 1, then this number is going to be less than this number, and then everything is going to be greater than this number. Okay. Now, and this is equal to what? So this is equal to 1 over n minus 1 minus 1 over n, right? So we have that 1 over n squared is less than this thing here, and these two guys here. Okay. Then look at this. What if we have this? So this 1 plus 1 over 4 is just, of course, 1 over 2 squared plus 1 over 3 squared plus and so on plus 1 over n squared, right? And for each of them, this holds. Then it means that this is less than 1. That 1 plus, we have to put here the case for 2. So 1 over 1, so 1 over 1 minus 1 over 2, right? So instead of writing 1 over 2 squared, we have to write 1 over 2 minus 1 minus 1 over 2. Okay, now plus 1 over 2, right? So 1, we have here 3 squared, so we have 1 minus 3 minus 1 minus 1 over 3 plus and so on, so until we get plus 1 over n minus 1 minus 1 over n, right? I think this is clear. And now look at this. So we have minus 1 over 2 here and 1 over 2 plus 1 over 2. So we can cancel these two things here. And we can cancel as well this thing with, here we will have plus 1 over 3 minus 1 over 4, right? So we will cancel this with this. And so on, we will cancel everything until we cancel. This is going to be the last thing we're going to cancel. And then we obtain that this is equal to 1 plus 1. So 1 plus 1 minus 1 over n. right? So 2 minus 1 over n, right? And we can see that this agrees with this, of course, right? Because we have that this sum, so this sum here is less than 2 minus something else. So of course this if they agree, okay? Now we actually can prove, we actually can change this, and we can add this thing here, right? Why? Because I'm showing you this, and this is a stronger statement than just less than 2. I'm showing you that it's not only less than 2, but it's less than 2 minus 1 over n, and I can write this 2, and then I'm going to prove something even stronger, okay? And why am I doing this? Because it's better, it's comfortable for me to do it. And in the proof, we will see that, okay? So let me just erase thing. Okay, somebody asked, could you please explain number 6 from homework? Well, if you have any questions about the homework, we can discuss that tomorrow, okay? So just, we can see it tomorrow. Then, okay, now, then let's prove that 1 plus 1 over 4 plus 1 over 9 plus 1 over n squared is less than 2 minus 1 over n. Now we can talk about induction here. And so by induction, let's prove this by induction on n, okay? So we have that this is the, okay, so prove that, well, we have to add here that n is at least 1, right? So we have that the basis step, I have to show the basis step, and it means that, so this is our phi, right? So that if this is true, then this holds, okay? Then we can check this, so it means that we have to check phi of 0, so that if 0 is at least 1, then something here holds, but we can see that this is false, right? This is false. Then it means that this is true, so this holds, okay? So it means that the basis step holds, right? And now what about the induction step? We have to show the induction step, and we have to show it for 2 cases. So in the, so I need to show phi of n plus 1, right? So let me write that to be clear. So I have to show that n plus, for n plus 1 at least 1. If this holds, then the sum from k1 to n plus 1 of 1 over k squared is going to be less than 2 minus 1 over n plus 1. Okay, so this is minus here. So this is that I assume that phi of n holds, and now I have to show that phi of n plus 1 holds, okay? And we have 2 cases. We have the first case is for n0, And for n0, we see that we cannot apply the induction hypothesis because n has to be at least 1, and we have n0. Then all we have to do, what universally what? Okay. So we cannot apply the induction hypothesis here. So this, right? So phi of n. We just have to put this value here, right? And then we get that for n0, if we put that here, so I have to prove that here, we obtain that 1 over 1, right? So this 1 has to be at least okay, we have to change something here. Let's prove it for equal. Okay, not only less, but less or equal. Okay, then we have to change that here, because if we don't do that, then it doesn't work. Okay, so let's this is okay. Then we need to, if we put this here, we obtain 2 minus 1, so 1, so this is 1. So we obtain that 1 is at least 1, so this holds, right? And the second case, and let me write that case over there. In the second case, we already can apply the induction hypothesis because n will be at least 1. So in the second case, we have that n is at least 1. Then here we can apply, so let's apply the induction hypothesis. And then we need to do what? We need to write this. So the sum from k1 to n plus 1 of 1 over k squared. So we have to show that this holds, right? And we know that this is equal to what? So this is equal to the sum from k1 to n of 1 over k squared plus 1 over n plus 1 squared, right? N plus 1 squared. So this is true, of course. And then by induction hypothesis, this is going to be at most 2 minus 1 over n, right? 2 minus 1 over n plus 1 over n plus 1 squared. Yeah. And then let's look at this. 2 things here. So this one. And we can see that this is equal to, well, this is equal to n squared plus n plus 1 over n times n plus 1 squared. So this is equal to this. Okay, and this of course is greater than n over n plus 1 over n plus 1 squared. So all we did was just we eliminated this 1 from here, right? We just take it out, this 1, and then we will obtain n squared plus 1, so n times n plus 1. Okay. So we have that this is greater than this, but since we have here minus, right? So we did this for this without the minus. It means that this is right. It means that or equal. This is greater. So this is at most 2 minus 1 over. So we have here n plus 1. Yeah. But we have that this is going to be less, strictly less than this, and we need that this has to be less or equal. Something. Okay, I have to check this. This has to be less or equal. Well, actually, if I just, so this should be then plus 1 over, yes, this should be plus 1 over n plus 1 square, and then I can write this minus this minus something, so this will be 2 minus 1 over n plus 1 minus 1 over n plus n times n plus 1 square. Okay. Well, I have to check this because I need to obtain here equal. Well, I can't, because if I have here equal, if I prove this thing, then this is not going to be true. Anyway, so this is the proof, but let me check this, and the next seminar I will can I ask questions from previous lectures? I think questions from lectures is better to ask to the lecturer. Okay, well, you can ask if you want, if it doesn't, it's not a long question. Okay, so somehow I have to fix this. I will check that, but this is the general idea of the proof. Okay, so let's say that this is proven, but anyway we have to check this. Okay, and that's it. So if we show this, then it means that we finish with the proof of number 7. Now, yes, we have time. Now we can move to number 8, and let me start here. From previous seminar. Okay. Yeah, sure. Ask. So this will be number 8. So in this case we have So we have that omega or W, I don't remember. Omega, let's go just. Omega is a binary word of length n. Okay, so we have a word. I'll send the picture in Telegram. Yes, please. So omega is a binary word of length n, right? And the following operations are allowed. So the first one, so we have a word and we can do the following with this word. So we can flip the first bit, right? Or we can flip the bit after the leftmost one. So of course, you know that, right? A binary word is a word, so it's a word in which we have only 0 and 1. So 0, 0, 1, 0, 1, 1, and so on, right? And this is of length n. Okay, and we can do the following with any such word. We can flip the first bit, so we can change this bit here. We can change it. So if we have 0, we can obtain 1, or if we have 1, we can obtain 0. And we can flip the bit after the leftmost one. So in this case, if we have 0, 0, 1, 0, and 1, we can change this bit because this one is the leftmost one, and then we can change the bit after this, so this one. So we can change this into 0, into 1, for example. Okay. How did you claim from the lower orange part the upper one? Okay, I don't. Well, we have to check the Instagram. I don't know what you're talking about. Okay, so flip the bit after. Yes. So we have a word of length n, and we can't. We have to. We are allowed to do two things to this word. Okay. And now we have to prove. So prove that it's possible to obtain any word of length n. So if we have a fixed word of length n, then applying only these two operations, then we can obtain any word of length n. So if we have a fixed word here, then we can change whatever we want here. We can obtain any word from this one. Okay, and we have to prove this. Okay, now well, so proof by induction, of course, on n, on the capital N. So we have to look at the length of the word, in this case is n, and we need to prove that for any value of this n, this holds. So let's take, so the basic step is n1 take n1, okay, because that's the last n we can have, just like 1. And then this is true, this holds, right? Because if we have just a word of length 1, then because of this condition, since we can flip the first bit, then if we have 0 or we have 1, we can get 1 from here or we can get 0 from here. Then in this case, the condition holds. Okay, the base step holds. Good. Now, the inductive step. So suppose that it's proven for n minus 1. So for n minus 1, if we have n minus 1, we can get any word we want. Now we have to show that, then let's show that it holds. So this property holds for n as well. Right? And we are going to do the following. So since we can obtain any word of length n minus 1, then let's get the following word: 0, 0, 0, 0, 0, and 1. We can obtain this if this is of length n minus 1, right? By the inductive hypothesis. So we can construct any word we want of length n minus 1. Let's build this one. So we have only 0, 1, and 1 here. And then because of this condition, of the condition number 2, so the leftmost one in this case is going to be this one. Then in the position number nth, so this is the nth position, we can put any number we want, 0 or 1. I mean 0 or 1. Because we have that this one is the leftmost one. So we can flip this value from 0 to 1 as we want. Now we have that in the nth position, we can obtain any value we want. And now we have to apply this logic to this thing here. Right? So we have somehow, if we want to change this one, then we need to get 1 here and 0 here, such that we can change this thing. Okay? And in the same way, we can, if we want to change this one, then we need 1 here and 0 here, such that we can change this thing. Okay? So this is the first step. And then we look at each of them, which do we need to change, and then we make all the needed arrangements. Okay? And that's it. So what do I need to show here? I need to show that, look, we change this value, the nth position, and then we have to change all these positions, right? And I have to be careful that if I change something here, it doesn't affect my values here. So if I change some m, so we have here m, if I change m bits here, I have to be careful that it doesn't change my bit n plus 1 and n plus 2, and that they will be not affect for the changes that I apply here. And of course this is true because I mean, how can this happen, right? So if we change something here, we are not going to touch these bits here. We only are going to work with these bits here until we obtain the last bit that we want. Okay? So, and that's it. Let me give you an example. So this is proven. But let me give you an example. For example, if we have this word 0, 0, and 1, and I want to get the word 0, 0, and 0, right? What do I need to do? So so I need to apply these two possible operations here in order to get 0, 0, and 0 from 0, 0, and 1. Then what can I do? What's the first thing I can do to this? Of course, I can change this thing here. So I can put 1, 0, and 1. So I change the first one, okay? Now I can change this 0, 1, this 0 here, and I can obtain 1, 1, and 1, right? Okay, and then I need to change this 1 here into 0. Then I need him to be next to the leftmost 1. So I need this to be 0. Then I can change this, right? The first one, so it's 0, 1, and 1, right? And now I can change this number. This bit here is going to be 0, 1, and 0, right? And now I need to change this 1 into 0 again. So I need to change this 0 into 1 in order to change this 1. So I can change 1, 1, and 1. 1, 1, and 0. And now I can change this 1 from here, and I will get 1, 0, and 0. And finally, I can change the first bit because of the initial condition, and I will get 0, 0, and 0. And so in this way, I can obtain any word of length n only applying these two operations. Okay, this is an example, and this kind of things that is the same that you need to do here. Okay, so you change the first one, you need to change the first one, and then you can change everything here into so you change this, then this, then this. For changing each of these bits, you will have to make some operations here. Okay, so this can be really long. How did you get 1, 1, 1? What? Where did I get 1, 1, 1? 1, 1, 1. Here. Well, I change. So in this case, I have a 1, 0, and 1. And what is the leftmost one? Is this one. This is the leftmost one. Then I can change the bit next to it. So I can change this thing. So I change this 0 into 1. And then I obtain 1, 1, 1. Okay, and so on, and that's it. So this is proven. Yeah. Now, I think we don't have much time. What other? I see. Okay, so yeah, the next. So we are left with exercise number 9 and 10. We're going to do it the next seminar, and I think that's it for today. I will be waiting for you tomorrow at 6 o'clock. Okay, have a good day. Thank you very much.